running rough on the lower cylinders.
Ignition harness, perhaps.
We'll need a closer look before takeoff.
These tolerances are unacceptable. The stress fractures match the fragment analysis.
Then the thermal expansion data is flawed. We must recalculate immediately.
Run her up again. Keep an eye on the pressure.
Pressure's holding steady. All green.
January 1940. Before dawn, the refinery is already awake. Steel towers rise out of the New Jersey cold, wrapped in steam that drifts low across the ground. Valves hiss. Pipes knock softly as crude oil moves through them, thick and reluctant in the winter air. Inside a small office near the cracking units, a desk lamp burns alone. Papers lie spread across the table. Test reports, engine specifications, handwritten notes smudged with oil and pencil graphite. They all point to the same problem. America has airplanes. America has pilots. America has oil. But America does not have the fuel those engines will soon demand. Across the Atlantic, British fighters are being pushed higher, faster, and harder with every passing month. German bombers are climbing on thinner air, running hotter engines, burning fuel refined for war. In the United States, aircraft manufacturers are designing engines that promise power the nation cannot yet reliably feed. High altitude means higher compression. Higher compression means knock. And knock, at 20,000 feet, means death. In this moment, before Pearl Harbor, before declarations, before slogans, the future of air war hangs not on wings or guns, but on chemistry, on whether liquid can be persuaded to burn differently, and whether time will allow it. The question leads directly into how the world arrived at this silent crisis in the first place. The problem did not appear suddenly in 1940. It had been forming quietly for a decade. In the early 1930s, aviation fuel was little more than gasoline with stricter handling. Most military and civilian aircraft engines ran comfortably on fuels rated between 70 and 80 octane. At low altitudes with modest compression ratios, that was enough. Engines rattled, vibrated, and leaked oil, but they flew. Then aircraft began to climb. As designers chased speed and altitude, compression ratios rose. Superchargers forced more air into cylinders. Higher air pressure meant more power, but it also meant instability. Fuel that ignited too early or unevenly could tear an engine apart. Pilot called it knock. Engineers called it detonation. Everyone understood the result. At 15,000 feet, it was a warning. At 25,000 feet, it was catastrophic. By the mid-1930s, this reality had already reshaped European air doctrine. The Royal Air Force, watching German aviation developments with growing unease, invested heavily in higher-octane fuels. British chemists and engineers pushed toward 100-octane aviation gasoline, not because it was convenient, but because it was necessary. Without it, modern fighters could not climb fast enough to intercept bombers or survive sustained combat. Germany followed a different path. Lacking access to abundant crude oil, the Reich invested in synthetic fuel production, converting coal into liquid hydrocarbons. The process was expensive and complex, but it allowed Germany to tailor fuels for specific engine needs. By the late 1930s, German aviation fuel quality was inconsistent but carefully managed, tightly rationed, and treated as a strategic weapon. The United States watched all of this from a distance. American oil production was vast. Texas, Oklahoma, California, crude flowed in quantities unmatched anywhere on Earth. Refineries were optimized for volume, not precision. Automobile gasoline dominated demand. The assumption was simple. If a nation ever needed aviation fuel, the oil industry would provide it. That assumption was wrong. High-octane aviation gasoline was not merely a refined product. It required controlled molecular structures, branched hydrocarbons that resisted premature detonation. Producing it in large quantities demanded processes most American refineries had never scaled. Thermal cracking could increase output, but it did not guarantee stability. Straight-run gasoline varied too widely in quality. Blending alone could not solve the problem. In laboratory tests, American engines showed promise. On paper, they could outperform their European counterparts. But again and again, test flights revealed the same limitation. Engines had to be throttled back to avoid knock. Altitude ceilings were theoretical, not practical. By 1938, this gap was no longer academic. Reports from military observers in Europe described air battles being decided not just by pilot skill, but by climb rate and sustained power. British fighters using 100-octane fuel could push their engines harder during combat. German aircraft relied on tightly controlled mixtures and careful maintenance. Fuel quality was shaping tactics in the sky. Inside the U.S. Army Air Corps, concern grew quietly. The service was small, underfunded, and politically constrained by neutrality laws. But its engineers understood the stakes. Without reliable high-octane fuel, any future expansion of American air power would be limited before it ever reached the enemy. The problem was not oil scarcity. It was refinement. By 1939, Europe was at war. Bombers crossed borders. Fighters rose to meet them. And in the United States, the question was no longer whether high-octane aviation fuel would be needed, but whether it could be produced fast enough and in quantities large enough to matter. That uncertainty pushed attention away from runways and factories and toward the structure of American industry itself. By the autumn of 1939, the war in Europe had clarified something American planners could no longer ignore. Air power was not an accessory to modern war. It was its opening move, and air power depended fundamentally on fuel. The United States oil industry was immense, but it was also fragmented. Dozens of companies operated thousands of wells and refineries, each optimized for commercial gasoline, lubricants, and heating oil. Aviation fuel represented only a sliver of total demand. Even within that sliver, military-grade high-octane gasoline was a niche product, expensive, difficult to standardize, and poorly understood outside specialist circles. Standard Oil of New Jersey stood at the center of this system. By 1940, it was not a single company, but a network. Refineries, research laboratories, overseas holdings, and technical licensing agreements that stretched from the Gulf Coast to Europe. Its engineers understood cracking processes better than almost anyone else in the world. Its chemists worked with hydrocarbons at a molecular level most competitors never touched. And yet, even within Standard Oil, 100-octane aviation gasoline was not a solved problem. Producing high-octane fuel in laboratory quantities was one thing. Producing it reliably, in millions of barrels, under peacetime political constraints, was another. The obstacle was alkylation. Alkylation was the key chemical process that allowed refiners to combine light hydrocarbons, such as isobutane and olefins, in a high-octane blending components. In theory, it was elegant. In practice, it was volatile, corrosive, and unforgiving. Early alkylation units suffered frequent failures. The acids involved, sulfuric or hydrofluoric, destroyed equipment if mishandled. Scaling the process required new materials, new safety protocols, and a tolerance for risk that most commercial refineries avoided. Before 1940, only a handful of American plants had operational alkylation units. Their output was small, their reliability uncertain. The industry had little incentive to expand them rapidly. There was no mass market demanding 100-octane fuel. There was no declared war forcing compliance. At the same time, political pressure pulled in opposite directions. The United States was officially neutral. Congress scrutinized any action that appeared to prepare for war. Arms exports were controversial. Fuel shipments were sensitive. Yet Britain, now standing alone against Germany, urgently needed high-octane aviation gasoline. British purchasing missions arrived quietly, armed with technical requirements and desperate timelines. American officials walked a narrow line. Publicly, there was no mobilization. Privately, conversations between the military, the oil industry, and the Roosevelt administration grew more urgent. If the nation waited until war was declared to solve the fuel problem, it would already be too late. Standard Oil's leadership understood this calculus. They also understood the risks. Expanding alkylation capacity meant massive capital investment. It meant retooling refineries that already made steady profits. It meant committing to a fuel whose primary customer, the U.S. military, could not yet guarantee long-term contracts. And it meant doing all of this under the watchful eye of regulators and critics who distrusted large oil companies on principle. Yet by early 1940, hesitation was no longer an option. Test data from aircraft engines made the consequences unmistakable. Without high-octane fuel, new American fighters and bombers would be forced to operate below their design limits. Range would shrink, climb rates would suffer, payloads would be reduced. In a war already demonstrating how quickly air superiority could be gained or lost, those margins mattered. So decisions were made not with speeches, but with blueprints. New alkylation units were approved. Experimental blends were tested relentlessly. Engineers worked around the clock to stabilize processes that had never been pushed so hard. What emerged was not a single breakthrough, but a coordinated effort, industrial, chemical, and logistical, aimed at reshaping how fuel itself behaved under pressure. Those efforts would soon be tested from multiple directions at once, because fuel was not just a chemical problem, it was a human one, and that truth becomes clearer when the story is examined from the angles of those who had to make it work. The work did not happen in boardrooms alone. It happened in laboratories that smelled of solvents and hot metal. Chemical engineers at Standard Oil and its affiliated research centers worked under conditions that rarely made headlines. Shifts stretched long past daylight. Test results were pinned to corkboards, crossed out, recalculated, pinned again. Every failure left behind warped metal, scorched seals, and the knowledge that a small error in chemistry could ripple outward into combat losses months later. These were not combatants, but they understood consequence. Many had aviation backgrounds. Some had watched test engines destroy themselves in seconds when fuel behaved unpredictably. Unlike aircraft designers, they could not simply reinforce a structure or add horsepower. Their task was invisible: persuade hydrocarbons to resist chaos under pressure. The urgency was quiet but constant. Britain's requests grew sharper. Army Air Corps specifications tightened. There was no single order that said solve this now, only a growing sense that delay itself was dangerous. By mid-1940, alkylation failures were no longer acceptable learning experiences. They were setbacks with strategic weight. And yet, the engineers stayed, because someone had to. At the center of the effort was alkylate, a high-octane blending component with properties ideal for aviation use. Stable, knock-resistant, powerful, but producing it safely at scale was a constant battle. Alkylation units operated under corrosive conditions that attacked steel from the inside. Temperatures and pressures had to be balanced precisely. Too little control, and the reaction stalled. Too much, and equipment failed violently. Early designs leaked, overheated, or shut down without warning. Standard Oil's advantage was not a single invention, but systems thinking. Engineers redesigned units to be modular. Materials were upgraded. Monitoring increased. Redundancies were added where accountants once resisted them. Output slowly became predictable. With each improvement, fuel specifications tightened. Octane ratings stabilized. Variance narrowed. The fuel no longer had to be treated gently by engine designers. Instead, engines could finally be allowed to perform as intended. This shift mattered more than horsepower figures ever suggested. It meant reliability under sustained stress, minutes of full throttle without detonation. It meant engines that survived long climbs and long chases. It meant confidence. Even before the United States entered the war, the tactical implications of high-octane fuel were becoming clear. Aircraft performance was no longer limited by airframe strength alone. With stable 100-octane fuel, superchargers could be used aggressively. Pilots could climb faster, reach higher altitudes, and maintain power longer. In air combat, these margins translated directly into advantage. Higher altitude meant earlier interception. Sustained power meant escape after engagement. Engine reliability meant fewer forced landings, fewer training deaths, fewer losses before enemy contact. These are not abstract benefits. Reports from British pilots flying American-built aircraft demonstrated measurable improvements once higher-octane fuel became available. Engines ran cooler at high power. Throttle response improved. Mission planning became more flexible. In the United States, test squadrons began to adjust doctrine accordingly. Fuel was no longer treated as a limiting factor, but as an enabler. Aircraft that had once been considered underpowered now met expectations. Designs previously shelved became viable again. Yet for all these advantages, the system remained fragile. Production had to scale further. Distribution had to be secured. And all of it had to happen before the political situation made delay impossible. Because behind every technical success stood decisions made by leaders and watched closely by enemies, who understood that fuel could decide wars long before the first shot was fired. No single executive announced the shift. No public directive ordered the industry forward. What existed instead was alignment. By 1940, senior figures within Standard Oil, the Roosevelt administration, and the U.S. Army Air Corps shared an understanding that remained largely unspoken. If aviation fuel production failed, everything built on top of it, airframes, training programs, strategic plans, will be compromised before combat ever began. Leadership expressed itself through permission rather than command. Regulatory barriers softened. Capital investments were tolerated. Technical information moved more freely between industry and government than neutrality laws officially allowed. This was not formal mobilization. It was preparation conducted in the margins. Executives approved expansions knowing profits might not come quickly. Military planners adjusted specifications knowing industry could meet them eventually. The relationship was imperfect, cautious, and sometimes tense, but it held. And in wartime preparation, holding mattered. Fuel was treated not as a commodity, but as infrastructure. While the United States struggled with scale, Germany faced a different problem: access. The Reich's aviation fuel came largely from synthetic production, derived from coal through hydrogenation and Fischer-Tropsch processes. These fuels could be engineered for high performance, but production was rigid and vulnerable. Facilities were few. Processes were complex. Output could not surge without warning. German aviation doctrine reflected this reality. Fuel was rationed carefully. Training hours were limited. High-performance operation was reserved for combat. There was little margin for waste, little room for error. In contrast, American planners began to envision abundance, not just sufficiency. If alkylation could be mastered at scale, fuel would no longer be the limiting factor in training or operations. Pilots could fly more. Engines could be pushed harder. Losses could be absorbed. This asymmetry, still theoretical in 1940, would later shape air campaigns far beyond what anyone yet realized. Standard Oil's role was not uncomplicated. The company had faced antitrust scrutiny for decades. Its overseas ties and licensing agreements were controversial. Critics questioned whether a private corporation should wield such influence over national defense. These concerns did not disappear in 1940. They were set aside, not resolved. Engineers understood the contradiction. They were working to enable a war the nation had not yet formally entered, within a corporate structure often accused of serving profit above principle. Yet the reality of the moment allowed little space for philosophical comfort. Fuel could not wait for moral clarity. What mattered in those months was output, reliability, scale. The decisions made in refining towers and research labs would shape outcomes thousands of miles away, in skies not yet contested by American pilots. By late 1940, the question was no longer whether high-octane aviation fuel could be produced in meaningful quantities. It was whether the system could survive the moment when theory met demand. That moment arrived when experimental success collided with operational necessity, and the margin for error disappeared. The transition from experiment to commitment did not announce itself with celebration. It arrived as a deadline. By mid-1940, demand for high-octane aviation gasoline had outpaced every cautious projection made only a year earlier. British orders increased sharply as the Battle of Britain intensified. American aircraft production schedules accelerated in anticipation of a war no longer considered hypothetical. Test data was no longer enough. Fuel had to move by rail, by ship, by pipeline, in volumes that strained existing systems. Alkylation units that had once been treated as experimental were now treated as essential infrastructure. Standard Oil and its partners moved to standardize what had previously been bespoke. Process variations were reduced. Blending formulas were fixed. Quality control protocols tightened until deviation became unacceptable. Refineries that had never produced aviation fuel were reconfigured to do so, often at the cost of interrupting profitable civilian gasoline production. The risk was substantial. Alkylation failures at this scale were not academic. A single leak of hydrofluoric acid could cripple a unit for weeks. A single miscalculation could contaminate entire fuel batches. Yet production continued, driven by a sense that delay itself was a form of failure. At the same time, engine manufacturers adjusted. Knowing stable 100-octane fuel would be available, designers recalibrated superchargers and boost limits. Compression ratios crept upward. Power curves shifted. Aircraft that had been throttled by uncertainty were allowed to perform. This was the true breakthrough, not a laboratory result, but a mutual commitment between fuel and machine. Data from test stands reflected the change almost immediately. Engines ran longer at higher power settings without detonation. Thermal margins widened. Maintenance intervals stabilized. Pilots reported smoother operation under sustained load. Behind these results lay thousands of small decisions. Valve materials changed. Monitoring instruments multiplied. Emergency shutdown protocols were refined. Each improvement shaved uncertainty from a process that could not afford it. By late summer 1940, 100-octane aviation gasoline was no longer scarce in principle. It was scarce only in volume, and volume was rising. The significance of this moment extended beyond numbers. It marked the point at which American air power ceased to be constrained by fuel quality. The bottleneck shifted elsewhere to production capacity, training pipelines, and strategy. But the system was not yet proven under the one condition that mattered most: combat. What happened next would determine whether this industrial effort had merely postponed failure or quietly prevented it. The proof did not come in a single test flight. It emerged in accumulation. As 1940 drew toward its close, reports from Britain began to change in tone. Aircraft using American-supplied high-octane fuel were no longer being flown cautiously. Pilots pushed engines to limits previously avoided. Boost pressures increased. Climb profiles steepened. The fuel behaved as promised. Not perfectly, but predictably. That predictability mattered more than raw performance. During sustained operations, engines held together. Detonation incidents declined. Maintenance crews reported fewer cracked pistons and burn valves. The difference was not dramatic in isolation. It was decisive over time. In the United States, Army Air Corps trials mirrored these findings. Test squadrons operating with standardized 100-octane fuel rewrote operating manuals. Emergency power settings became routine options. High-altitude performance matched design expectations. For the first time, aircraft, engines, and fuel existed in balance. This balance altered planning assumptions almost immediately. Training programs expanded. Pilots logged more hours at combat power. Formation tactics were refined with confidence that engines would respond uniformly. Attrition rates in training, long a silent drain on readiness, declined. Behind these operational shifts was an industrial reality few outside the system saw. Refineries ran continuously. Supply chains tightened. Railcars and tankers moved with new priority. Every interruption carried the risk of cascading shortages. And yet, the flow held. By the end of 1940, the United States had done something quietly unprecedented. Without formal mobilization, without declarations, it had created a fuel system capable of sustaining modern air war. Not in theory. In practice, this achievement did not win a battle. It did not stop a bombing campaign. It did something subtler and arguably more important. It removed uncertainty. When a nation would finally be forced into open conflict, it would not discover, too late, that its aircraft could not be pushed to their limits. That discovery had already been made, tested, and resolved in refineries far from any front line. The turning point was complete not when the first engine survived full throttle climbs, but when planners stopped asking whether fuel would hold. They began asking how best to use it, and that shift reshaped everything that followed. The effects of high-octane fuel availability appeared first in numbers that rarely reached the public. Aircraft performance charts changed. Training accident reports declined. Maintenance cycles stabilized. None of these shifts carried dramatic headlines, but together they transformed readiness. With standardized 100-octane aviation gasoline now moving through supply channels, American aircraft manufacturers finalized designs that had previously existed in cautious drafts. Engines were cleared to operate at higher boost pressures. Bombers carried heavier loads without sacrificing range. Fighters reached interception altitudes faster, with less mechanical penalty. The U.S. Army Air Corps, still modest in size, adjusted its planning assumptions accordingly. Sortie rates increased. Training syllabi expanded. Pilots spent more time flying at combat power rather than conserving engines. The difference was not merely technical, it was psychological. Confidence replaced restraint. This confidence extended to logistics. Fuel planners, once forced to hedge every estimate, could now calculate consumption with greater certainty. Reserve stockpiles grew. Distribution networks hardened. By the time of America's formal entry into the war in December 1941, aviation fuel shortages were not among the service's immediate crises. The impact was felt beyond American forces. British reliance on imported high-octane fuel eased as U.S. production increased. RAF aircraft, already designed to exploit such fuel, benefited directly. Improved climb rates and sustained power influenced interception outcomes during critical periods. While fuel alone did not decide air battles, it shaped the margins within which those battles were fought. Industrial data reflected the shift. Alkylation capacity expanded rapidly through 1941. What had once been experimental infrastructure became standardized across multiple refineries. Output rose not linearly, but exponentially, as processes stabilized and replication replaced improvisation. Importantly, these gains were resilient. Damage to individual units no longer threatened total output. Redundancy, once seen as wasteful, became standard practice. The system learned to absorb shocks. The immediate aftermath of the breakthrough was not celebration, but normalization. High-octane aviation gasoline ceased to be treated as an exotic specialty. It became baseline. And in warfare, what becomes baseline quietly defines what is possible. That normalization carried consequences far beyond training fields and factory floors. It altered how strategists thought about air power itself, and how enemies would struggle to respond. Those consequences unfolded over time, reshaping the broader balance of the war. As the war expanded, the true significance of America's aviation fuel solution revealed itself not in isolated engagements, but in sustained operations. By 1942, the United States and its allies were flying more sorties for longer durations at higher power settings than any Air Force had previously attempted. This intensity depended on engines that could be pushed repeatedly without catastrophic failure, and on fuel that behaved the same way every time. High-octane abundance made this possible. Strategic bombing campaigns demanded long-range flights at altitude, often in formation for hours. Fighters required sustained climb and chase capability to escort bombers deep into contested airspace. Training pipelines consumed enormous amounts of fuel before pilots ever reached combat. None of this could function under conditions of scarcity or inconsistency. In contrast, Germany's fuel situation grew steadily worse. Synthetic fuel plants, already stretched, became prime targets. Production was vulnerable to disruption. Output could not surge to meet demand. Even when high-quality aviation fuel was available, it had to be rationed carefully. Training hours were cut. Replacement pilots arrived at the front with fewer flight hours. Aircraft sat grounded not for lack of airframes, but for lack of fuel. This asymmetry widened as the war continued. Allied air forces treated fuel as an enabler of pressure, something to be expended aggressively. German planners treated it as a constraint to be managed defensively. The difference shaped outcomes. American aircraft design philosophy evolved in tandem with fuel certainty. Engines grew larger. Supercharging became more ambitious. Reliability assumptions shifted. The expectation was no longer that fuel quality would limit performance, but that fuel would support whatever performance engineers could safely design. By the later years of the war, this assumption underpinned air dominance. It allowed flexibility in tactics, resilience in losses, and endurance in campaigns that stretched across continents. All of it traced back to decisions made before the war began, when there was still time to build systems instead of improvising under fire. The strategic consequence was not simply that Allied aircraft were faster or more powerful. It was that they could afford to fly more, train more, and lose less to mechanical failure. Fuel did not win the war alone, but it ensured that air power could be applied without hesitation. That realization invites reflection, not on chemistry or industry alone, but on how wars are shaped long before they are officially declared. The story of high-octane aviation fuel does not fit comfortably into traditional narratives of war. There is no battlefield, no decisive charge, no moment of visible triumph. Its importance is measured instead in absence, in engines that did not fail, in aircraft that reached altitude when they needed to, in pilots who returned because their machines held together. In 1940, the United States faced a contradiction it did not yet fully acknowledge. It possessed immense industrial power, but not in the form modern war demanded. Oil alone was not enough. It had to be transformed, controlled, and trusted under conditions far beyond peacetime use. Standard Oil's role in that transformation was neither heroic nor simple. It was technical, cautious, and driven as much by pressure as by foresight. Yet the result mattered. High-octane fuel changed what American and Allied aircraft could safely attempt. It turned theoretical performance into operational reality. This shift reminds us that wars are often decided before they are fought, by infrastructure rather than tactics, by preparation rather than reaction. When combat finally came, the United States did not discover a fatal weakness in its air power. That weakness had already been confronted, refined, and removed in refineries months earlier. Fuel is easy to overlook because it leaves no monument. But in the Second World War, chemistry quietly shaped the sky. The ability to burn liquid a little differently to delay ignition by fractions of a second, opened altitude, speed, and endurance that altered the course of aerial warfare. In the end, victory did not hinge solely on courage or strategy. It rested on whether an engine could be trusted at full throttle, in thin air, far from home. And that trust was built long before the first bombs fell.